Hi again. I didn't realize that I was running out of time, so let's just go back and finish up number 64 here. So as I finished on the last video, the first derivative will be above the x-axis before 2 and increasing at the same time. Above the x-axis, pencil headed up. Then to the right of 2, the graph of the first derivative needs to be below the x-axis, but our pen will be going up at the same time. So if we extend the vertical asymptote, below the x-axis, increasing function. So on the right-hand side, it's a reflection of the original over the x-axis. Now what do we know about the second derivative? The second derivative is strictly positive, so the graph will be above the x-axis. So the second derivative will pretty much lie on top of the original function, just as the left-hand side of the first derivative was on top of the function. And that's it for the graphing of those four. Okay, so let's go back to the four things that I mentioned at the very beginning of the first video. Characteristics of the graph of a function, and a complete list can be found on page 209 in your textbook. Domain and range, x and y intercepts, vertical and horizontal asymptotes, and discontinuities. Now, all of these we've studied already. Okay, at the end of your chapter 1 test, after we learned everything about limits, if you go back to your test, you were asked to graph two functions. Well, now we can just make those functions more accurate, or we can at least determine, we can understand what the intervals of increasing and decreasing are from the information that we've learned presently in chapter 3. We're only going to do two graphs here because you guys are going to see, once you get the specific information, either determining intervals of increasing, decreasing, and concavity, or a couple pieces of information, domain and range and intercepts, you'll be able to very loosely sketch a function. What we do specifically is interpret the derivative and the second derivative given the graph, or we interpret the function given the graph of the first derivative. So I'm only going to look at two examples for this so you can see how it all gets put together. Alright, I'm in section 3.6, page 215, and this is number 8. Y equals x squared plus 1 all divided by x squared minus 4. Okay, so what's the domain of the function? Lost my pen. We know we can never have 0 in the denominator. So x equals plus, or x can't equal positive or negative 2. More specifically, what do they become on the graph of the function? Vertical asymptotes. Because if we did a direct substitution back into the original, we would get number over 0. Now the range is not as easy to determine, and we can sort of determine the range if we're given the graph, but we won't look specifically at finding what the restrictions on the y values are. Okay, x-intercepts, set y equal to 0. Where does that occur? In a rational expression where the numerator is 0. We can't solve that equation for x, so no x-intercepts. Y-intercepts, set x equal to 0. So we have a y-intercept at 0, negative 1/4. Horizontal asymptotes, again going all the way back to chapter 1. They came from limits at infinity. Limits at infinity is when we learned our shortcuts. And the shortcuts were top heavy, bottom heavy equal. The exponents on the top and bottom here are equivalent. So we only need to compare their coefficients. Dividing x squared by x squared would give us a limit of 1 for both as x approaches positive and negative infinity. So this tells us that we have a horizontal asymptote at the line y is equal to 1. Now, at the end of chapter 1, this is all the information we had. Vertical asymptote, horizontal asymptotes, y-intercept at 0, -1/4, no x-intercepts. Now, to determine the behavior of the function around the vertical asymptotes, we looked at the one-sided limits. -2 from the left, -2 from the right, +2 from the left, and then +2 from the right. Now, if there's no x-intercepts, then the graph can't cross the x-axis at all. So using the characteristics of the asymptotes, we can verify from the one-sided limits that this is what the graph would look like. Well, let's just look quickly, not overly quickly. Let's determine the first and second derivatives to verify the intervals of increasing, decreasing, and concavity. And this will be good practice for your derivatives as well. X squared plus 1 all over x squared minus 4. First derivative, bottom, times the derivative of the top function, minus top, times the derivative of the bottom, all over bottom squared, distributing the 2x, then distributing the 2x and the -1, don't square the denominator, they cancel, -10x. Where does the derivative equal 0? When the top equals 0. Where does the derivative not exist? When the bottom equals 0. So on a labeled number line. Okay, our denominator is always going to be positive because we're squaring the denominator. If we plug -3 in, positive numerator, -1, again positive numerator. +1 would make negative in the top. Anything greater than 0 would keep a negative in the numerator. Now, -2 and 2, we know already are our vertical asymptotes. That's why we have to keep those on the number line. So, my function, increasing, increasing, decreasing, decreasing. At 0, we would have a relative max. Where does a relative max occur? Plug 0 back into the original function. What did we determine this to be? We already know that that's the y-intercept of the function. Alright, let's look at the second derivative. So y prime was -10x. Second derivative, bottom times the derivative of the top, minus top times the derivative of the bottom, using power and then chain rule, all over bottom squared. X squared minus 4 will cancel from each term in the derivative function. -10x squared plus 40, +10 times +10x times 2, +20x times another 2x would give us a +40x squared. Combining like terms, where does the second derivative equal 0? We would be attempting to solve this equation, which doesn't exist. Where does the second derivative not exist? Plus and minus 2. Our numerator now will always be positive because we're squaring the value of x and then adding 40 to it. If we plug -3 in, 9 minus 4 gives me a positive, making that interval positive. If we plug in 0, it'll make the denominator negative. And then this last interval will again be positive. So we have concave up, concave down, concave up. Okay, so let's go back to what we already sketched. Okay, so from y prime, we determined that y was going to increase and then decrease. Pencil going up before -2, pencil going up between -2 and 0. Pencil going down between 0 and 2, pencil continuing to go down after 2. From the second derivative, we determined the concavity of the function. So we said function was concave up to the left of 2, concave down between -2 and 2, concave up again. Concave up, concave down, concave up. So we didn't need the first and second derivatives in there, but it enables us to verify the information just using the properties that we learned in chapter 1. Okay, let's look at a polynomial function. Where is this one? Number 27. Y equals 3x to the 4th plus 4x cubed. I'm not going to have enough time to finish this one. Domain, it's a polynomial, all real numbers, no restrictions. X-intercepts, set y equal to 0. Factoring out an x cubed, 3x plus 4, 0 and -4/3. Y-intercepts, set x equal to 0. So 0, 0 will be a y-intercept. No vertical asymptotes. No horizontal asymptotes. So just looking at that information, y-intercept and x-intercept here, x-intercept at, if we make these -1 because I know what the graph looks like. Okay, that's all the information that we have just based on what we could determine from chapter 1. So it doesn't do us any good. It appears that it would be parabolic in shape because there's 2 x-intercepts. Knowing some basic properties of a polynomial, we know they're continuous functions, but it doesn't tell us where the increasing and decreasing change, if there's any changes in concavity. So what I would like you to do, complete the sketch of this graph. Determine the first derivative, increasing, decreasing relative extrema. Determine the second derivative, concavity, points of inflection, and then putting all of this together, sketch the function. So in class on Monday, I'll check this as well as the y coordinates of the relative extrema from the last example on the day 5 video. Enjoy your weekend.